Okay, so good morning, everyone, those joining us from wherever you are in Europe or beyond. So it's a pleasure with the EMIRI team to start this event on hydrogen with a focus on storage and distribution. I think that we are close to 100 for the day today. I'm checking with the Gemma. So it's a quite important topic that seems to attract a lot of interest. So we hope that you will enjoy the morning session and the afternoon session, which are different, but Marcel will give you a first flavor of how we structure the day. And I hope that this is going to be valuable for you. So here we are. My name is Fabrice Stassin from UMICORE. I'm also on the board of EMIRI, and it's a pleasure to welcome you. I have just a few slides on EMIRI for those of you who are not aware of who we are or are not involved too much into EMIRI. I will give you a quick update, and then I will give the floor to Marcel. So here we are on the Tech Talk. So this is a concept that we launched some while ago, focusing each time on different technologies. We have launched the focus group on hydrogen late of last year, so 21. And over the year, we have already had this year a focus group on Tech Talk on electrolysis. Now we're having one on hydrogen storage and distribution. And early next year, you can already pencil down the date on 19 January, we will be having one on fuel cells. So by doing so, we will have covered the main pillars of hydrogen technology. And then going forward in 2023, we will, of course, have recurring meetings on the topic. For those of you who would be in a batteries business, some of you are also in that business, we will have on the 29th of November, a tech talk on solid state batteries, which is, of course, a very important topic today. So quickly about EMIRI. EMIRI is the Energy Materials Industrial Research Initiative. It's, if you want to make it simple, the voice of those who are producing materials in Europe, the voice in Brussels, and of course also the voice of those who are using materials. And we try to be as open as possible. So industrial members we have, but we also have a very strong presence of the usual, I would say, research and technology organizations that are across Europe, that you all know, some of you, and some of you may be coming from some of them. The purpose that we have is to also make sure that in the European Commission and also the member states, there is a constant awareness of how crucial advanced materials are to make this energy and mobility transition possible. So what you have on this busy triangle in the left is that advanced materials are actually at the center, and it's also a vector to transform the industrial sector, which is very important also, for example, today in the discussions on critical raw materials. Advanced materials are connecting the critical raw materials to the application. So they are just in the middle and they have to receive the right level of attention. So this is really what we do at EMIRI. We try to make sure the awareness is there and that the policy initiatives of the Commission are as much as possible supportive of the ecosystem of advanced materials. I would say a couple of elements. We are industry driven. There's a majority of research organizations, but they all understand that we are here defending, I would say, research and development or innovation that comes at a moderate to high technology readiness level. So I would say from 3, 4 up to 7 when it comes to EU support. There are other clubs which are, I would say, pushing for the more fundamental part with whom we work, but we try to focus on what we do the best, which is industry-driven and industry-supportive research. We try to be as much fitting the strategy of the EU as possible. So we try to shape and implement their policies. For example, EMIRI is one of the leading forces behind the Advanced Materials Initiative 2030 of the Commission that you may have heard about, which is there to shape the vision for 2030. So this is typically what we do. On innovation ecosystem, we collaborate with public institutions just to make sure that the priorities that are going to be funded by the European Commission, by the member states, are the priorities that you guys have. So we are just there to defend the priorities that you have and to make sure that the money made available is money that you can use. Of course, we are also a network catalyst. We try to bring people together. It has not been so easy during the COVID year, to be honest, but now we are out of this as much as I can hope. And we are doing more and more things online. But of course, we are moving towards a few events that are in a face-to-face mode. And we are actually 10 years old. So last year in June, we celebrated the anniversary. So we're going strong, and it's something that has been there for some time. And it's also in line with the fact that to influence Brussels, you need a lot of patience and things take time. So it's good that we are continuing that work. I think that maybe on this slide, the most important for you to know is that we are, in the name we have energy, but we are also more than energy. It's energy, and it has become energy and mobility. When we were founded, we were focusing on energy, but now it's energy and mobility. And we are covering the focus areas that you see on the right. So it's 7 of them: batteries, hydrogen, solar technology, wind, low carbon industries. So it has to do more with all the materials that can be needed in order to decarbonize processes. Still connected to mobility is reducing the weight of the mobility applications. And last but not least, something dealing with more energy efficiency of buildings. And I think that it is done for my part. I will give the floor to Marcel. And if after this you have a couple of questions, we will be happy to take them before we go into the experts presentation. Thank you so much.
Good morning from my side. I'm Marcel Meeus. I'm technical advisor to EMIRI, so I belong to the EMIRI group. And let's see what we are going to do today. As Fabrice said, there has been already a similar workshop early this year in May on hydrogen production technologies. But today we are going to do the same exercise for hydrogen storage and distribution. On those technologies, we have made 6 technology sheets, one on compressed hydrogen, another one on liquid hydrogen, ammonia, hydrides and sorbents, liquid organic hydrogen carriers, and finally on pipelines. What do they include those technology sheets? They have first a short description of the technology. Then we give the state of the art and the future targets at system level of those technologies. Next, and based on discussions that we had before in the focus group, we give an overview of the different technology challenges and a first series of advanced material solutions. And then lastly, we have done a prioritization of those challenges and a bit of specific focus on the advanced material solutions. These are 2 examples or extracts from examples of those technology sheets. You see at your left-hand side the one on compressed hydrogen, on board and for transport. We describe the different systems, and next we go into the system KPIs, etc. And at your right-hand side, you see the similar one, the other one on hydrides and sorbents, describing the different materials and their challenges. So that has been done so far, a first version of the 6 technology sheets. Here you see an example of that prioritization work. On the left-hand side, the different, for compressed hydrogen, the different technology challenges. Reduce hydrogen embrittlement, increase the storage efficiency, etc. And those challenges have been voted within the focus group, and weight factors have been given to different challenges. You see them from 100 to down to 20. And the first series of advanced material solutions has been proposed. So what are we going to do today? In the morning session, and that is open to all of you, we will have experts from the different European RTOs, companies, to give us a technology update on those 6 different technologies. And the afternoon session, being restricted to the EMIRI members, we will have a workshop aiming to identify the most promising advanced material solutions, KPIs, for those technologies, and a review of the technologies. We will, for those technology sheets, first identify per technology the advanced material KPIs, most impactful for the system KPIs, and then select a top 10 of these KPIs, advanced material KPIs. We will try to put values on those KPIs, state-of-the-art and future targets, short-term and mid-term. The final purpose being to build a qualitative matrix showing the relationship and impact between the advanced material KPIs and the system KPIs. And that's what we call a heat map. This is an example of that heat map. You see the different KPIs on advanced materials and their relationship with system KPIs. But after that, the next steps, we will then update those technology sheets with the selected key advanced material KPIs, including the values, and we will try to make a heat map with the links between advanced material and system KPIs. This is the program for today. We will have in the morning session an update on EMIRI. Yeah, that's what we're doing now. The next item will be a presentation on compressed hydrogen storage, and I will do that myself as an introduction. Then we will have a presentation on liquid hydrogen storage by Dr. Davide Duri from CEA. We will have next a presentation on ammonia by Professor Earl Goetheer from TNO, followed by a short coffee break to continue by 11:30 with a presentation by Dr. Felix Heubner from Fraunhofer on hydrides and sorbents. On liquid organic hydrogen carriers. And finally, with Professor Depover from the University of Ghent, and a presentation on pipelines. Karim here, member of our group, will try to make a short wrap-up at the end of the morning session. That's for the morning part. In the afternoon, the workshop with the EMIRI members, including the review of the present status of the different technology sheets, where we are now. Then work for each of the technologies to try to define the KPIs and material solutions. If possible, if the time allows, identification of a first series of target values on the selected KPIs. And then if again, the times allows for it, a first version of the heat map. So these are the presenters, myself, Davide Duri, Earl Goetheer, Felix Heubner, Ton Janssens, and Depover. A few words on our group, focus group. We are about 80 members with good industrial presence. You see here the names, Solvay, UMICORE, NG, etc. And a series of well-known research and technology organizations. So we are about 80 members. The focus group is led by Fabrice Stassin, with as co-leader Karim Sidi Ali Sherif, and I'm doing a little bit of technical work, the technical advisor to those two gentlemen. Karim did it, what we do today for production in May. Fuel cells is announced for January by Fabrice, and today we are doing the storage thing. The purpose is to define smart key performance indicators, smart meaning specific ones, measurable ones, attainable ones, so realistic ones, relevant ones, and time-based ones. And that's what we will do in the afternoon. Here you see an example. We prepared an Excel sheet for each of the technologies with the challenges, their weight factor, and a first, let's say, pre-population that we did with KPIs, possible KPIs, and possible units. But the word will be with you in the afternoon to complete the full picture. Here again, the heat map example, and that was the introduction. Thank you. Are there any questions on this introduction? If not, we go to the presentations. So I'm the one to start the series of presentations, and I will give you not an academic introduction, but a more practical introduction on compressed hydrogen storage and distribution by focusing on the tank materials. So what are the tank requirements in compressed hydrogen storage? You know, it is a whereby hydrogen gas is kept under pressure to increase the storage density. And what are the specific requirements to compressed tank storage? That is, and importantly, the leak tightness of the system. System has to be compact in construction, needs to have an adequate weight for the application, and more importantly, a high fatigue resistance, meaning that the tank has to be filled, emptied, refilled many times, 10,000, 11,000 times. So we're talking about the number of cycles in the operation of the tank. And then it will come as a red line through the presentation, bringing solutions for the risk of hydrogen embrittlement. They need to be considered in the design of the tank. We see two major applications being at the right-hand side, integration in cars, the onboard storage, and secondly, the stationary storage on the left-hand side, or storage by or transportation in tubed trailers. What are the different tank metrics that we need to consider, and also in the KPIs in the afternoon? That is the tank inner volume by liters, the operating pressure of the tank in bars or in pascals, the mass of hydrogen that can be stored at that specific operating storage pressure in kilograms. So, for instance, 5 kilogram hydrogen in the fuel cells, in the fuel cell cars, the operating temperature range in degrees of Celsius, the maximum allowable pressure for the bar for the tank in bar or pascal, the mass of the tank in kilogram, external dimensions. As said before, the number of cycles allowed before overhaul. Lots of work is done on certification for safety for those vessels and the different tank types. What are the different designs and mountings for compressed tank storage? On the left-hand side, you see the space of hydrogen that will be filled, and the liner around that space, in fact, is decreasing or blocking the permeability of the hydrogen, and that liner can further be enclosed by an outer wrapping for high pressures, and that outer wrapping serves as load bearing and as insulation layer. Left-hand side, you see the neck of the tank where the hydrogen gets inserted, extracted, and connected to the hydrogen tank valve. In all cases, it also includes a safety valve. Optionally, right-hand side of the picture, there is an end plug as a secondary opening on the tank, but that is optional. That tank can be mounted in two ways, and more importantly here, the design for stationary storage and for jet trailers can be mounted by neck with a tight fixture at the neck side, or can be strap mounted with straps around the tank vessel. We have different tanks types, and those are the four main designs. We are talking about type 1, type 2, type 3, and type 4. Type 1 is the all metal version, 200 bar pressure. Type 2 is the metal vessel, but with a outer wrap of carbon fiber reinforced polymer layer, and that goes up to 300 bar. In the type 3 and type 4, we come into the mobility section, focusing 700 bar, and that can be in the type 3 version, a metal liner combined with the CFRP layer, and type 4 is a plastic liner, the same with the same outer liner of carbon fiber reinforced polymer. In a little bit more detail here, type 1 are all metal vessels that they store only about 1% of hydrogen at 200, 300 bar. The type 2 is a metal hoop-wrapped composite cylinder, weighing less than the previous one, and type 1. And as said before, types 1 and 2 vessels are unsuitable for vehicle applications due to their lower hydrogen storage density, heavier weight, and because of, we are talking about metal containers, because of the risk for hydrogen embrittlement. Type 3 and 4 are the ones for integration in fuel cell cars. 3 comprises the fully wrapped composite cylinder with a metal liner, and that metal liner is mostly made of aluminum alloys. And the type 4 is the same wrapped composite cylinder, but this time with a plastic liner. And that plastic liner is typically high-density polyethylene, acting as the hydrogen permeation barrier. The composite overwrap serves as the load-bearing structure and is typically made of carbon fiber or glass fiber composite, and this in an epoxy matrix. But there is a fifth one in development, and that is the type 5, no liner, all composite version. It's not ready yet for commercialization. It offers the highest potential for lightweight construction, and it might be interesting, for instance, for space applications. The difficulty still with type 5 tanks is with the risk for formation of cracks and to have effective solution for limiting and blocking hydrogen permeation. Microcracks in the laminate are already sufficient to increase or to start leakage formation. So we are EMIRI's advanced materials. What are the advanced materials used in compressed hydrogen storage in the types 3 and 4? The metal liners being steel, but mostly or generally aluminum alloys. The plastic liners as the barrier being high density polyethylene or aliphatic polyamides. For the outer wrap, fiber reinforced thermoplastics, and that can be carbon peak, polyether ether ketones, or carbon PA6, that's a nylon composition, nylon 6, and carbon PPS, and that's a polyphenylene sulfide. So these are the different reinforced thermoplastics wrap materials. There are also thermoset-based composites, glass fibers, and basalt fibers. When talking about hydrogen, storage of hydrogen, compressed hydrogen, safety testing is of utmost importance, and all types of vessels should be designed, manufactured, and tested in relevant codes and standards. And there is a lot of testing possible with compressed hydrogen tanks. I give here simply a few examples. There is the bonfire test, and the tank shall vent through the thermally activated pressure relief device and shall not fail when exposed to such a fire during 20 minutes of duration. So there is a fire test done on the tank device. There are hydrostatic burst tests done, and typically the pressure at which the tank burst should be more than 2.2 times the working pressure. There is ambient pressure cycling test. The tank shall not fail before reaching more than 11,000 fill cycles, and that represents roughly 15 years of use in commercial heavy-duty application. There is the famous nail test, penetration test, that should be done and safely done. And the goal of all these tests is that the tanks should vent and not rupture. Word that has been fallen already a few times is hydrogen embrittlement. Hydrogen embrittlement or hydrogen assisted cracking, hydrogen induced cracking is a reduction of the ductility of a metal due to absorbed hydrogen. Hydrogen atoms are indeed quite small and can permeate through the solids. And once absorbed, hydrogen lowers the stress required for cracks to be initiated and propagated into the metal, resulting in embrittlement. Hydrogen can diffuse into the metal, react at the grain boundaries, can react in the voids, can react in the dislocations in the metal structure as a whole. Steels are quite prone to hydrogen embrittlement. Copper, aluminum, and stainless steels are less sensitive to hydrogen embrittlement. As said before, we have in previous work in the focus group for compressed hydrogen defined with about 80 experts a list of challenges on tank cost, challenges on mechanical stability, thermal stability, storage efficiency, hydrogen embrittlement, etc. We have discussed their impact, and we came with the first series of new advanced material solutions. That will be more completed in the afternoon with the EMIRI people and specialists working on this specific item. Let me end this presentation by showing you that Europe has already a strong value chain in compressed hydrogen storage. We have an impressive list of producers of tanks for compressed hydrogen already. You see the names that you know: Air Liquide, Linde, Praxair, McPhee, Plastic Omnium, etc., etc. It's a non-exhaustive list. So many people are already producers in Europe of compressed hydrogen tanks. There are already quite a lot of people, companies supplying materials to those manufacturers for the fibers, the carbon fibers, in polymers, the outer layer. We have several companies already supplying the composite materials, Cevoltech, Carbon, Void, etc. And for the liner material, the inner one, be it polyethylene high density or polyamide, we have Solvay, we have Arkema, we have Nov, DSM, etc. Several companies already excellently doing the job for this sector. And for the types 1, 2, and 3, for the composites, we have the same names, and metal liner companies, for instance, are Hydro and Lexer. That's the introduction. Thank you very well to compressed hydrogen. I don't know if there are questions.
There's one you can see in the chat.
Yes, I would have a question about the safety check in a fire. So how do you actually vent a bottle of hydrogen if there is a fire around? So what do you do with the safety valve, and how do you actually conduct the hydrogen away from the critical places?
That is a question to be asked to the producers, but I believe the gas is vented through that pressure relief system, and that is what they are testing.
Okay, so.
Maya, you have a question.
Yes, I would like to know how do you think that could be the best way to avoid the hydrogen enrichment by coatings protection, or how are you suggesting?
By the embrittlement is in fact governed by the layer, by the used, and in fact the embrittlement is less less present in the aluminum liner because aluminum is less sensitive to enrichment, and it is also less present with the polymer liner which is used in the focus tanks. And for the steels, then if it is no steel tank, then it will be people are working on different steel composition. And stainless steel, for instance, is less sensitive to everything.
I think we have time for one last question. There was a comment.
Thank you.
There was a comment on the water caverns.
No, no. No, it doesn't include rock caverns, no.
We focused on technologies to operate advanced.
Yeah. Our focus is on advanced nuclear solution.
We have a comment about the sound. Can everyone hear us okay?
Is there a problem with the sound? No.
Okay, so if everyone can hear us well, I propose that we move to the next presentation for the sake of time. And anyway, in the afternoon, for those of you who are there, we have time to go over and over discussions about innovation. But let's move to the next one. Marcel, I'll let you introduce.
And the next one is Dr. Davide Duri, and he is going to present us the storage as liquid hydrogen.
You are muted, Davide. Can you unmute yourself, please?
Is this okay right now?
Yes.
Okay. So thank you for having me. First of all, for your invitation. Can you see the screen? It's okay.
Yep.
Okay. So what I'm going to present to you is a broad overview of the liquid hydrogen storage, and especially focusing on the challenges and the hurdles that are linked to the storage, use, handling of liquid hydrogen. So the context is, everybody knows already the context, so I won't spend too much time on it. But the goal of this presentation is to give you an highlight, an idea, or some order of magnitude about the challenges that are related to structural materials. Basically, explain to you the functional issues related to the life cycle of a tank when liquid hydrogen is stored, in order to look at the safety issues, the functional issues, and then to derive the material selection, which is depending on the usage that we have for the tank, which is the best material that can be used. And next, the trends and what is missing in this in the development of these liquid hydrogen tanks. So we knew, everybody knew in the panel, I guess, and also in the audience, the hydrogen, the molecule of hydrogen. But when we are dealing with the liquid hydrogen, we have to be a little bit careful, since we are dealing with the extreme low temperatures, the lowest temperature that can be obtained except for helium, and this means that there are several issues of material properties that change quite significantly with the temperature. And we have issues of solidification, basically of all chemical species, except for helium, of course. We will have a densification if there is a bed, if there are cracks, or permeation in a linerless container. We have a densification on the other side of the tank, so we can have issues of chemical compatibility and risk of ignition in such condition. And then we have also to be as the only gas, the only chemical species which is compatible, which maintain its let's say its properties, is helium. We have to be also aware that helium is a fossil resource, very scarce, very costly, and therefore we have to design, we have to think about how to minimize the use of helium when handling hydrogen, when preparing, purging or venting a tank. Safety hazards, of course, as a paramount, in terms that we have to deal with the issues of frost, very low temperature, ignition energy, which is very low, about 20 millijoule before starting a detonation of the mixture, if there is a release in the atmosphere of sufficient energy. And also we have to deal with, in the case of an emergency, when we have a spilling of hydrogen, with also the risk involved with the detection and of flames, because they are transparent to the naked eye, and we have with very low radiant infrared emission. So there are strict safety regulations that are right now involved when dealing with hydrogen. Basically, for storage capacity above 5 tons, we have in Europe, we have to deal with the Seveso class regulation, which imposes very strict control and barriers and regulation on the use and handling of this liquid. So the requirement of what material can be used for a tank is of course driven by the user. I've classified three, let's say two major classes. So the ground installation for storage of larger, let's say for heavy user with storage capacity larger than 10 tons. It's an order of magnitude, of course. I don't pretend to be exhaustive in this analysis. And then mobile users, which can be earthbound, ships, trucks, automotive application, aircraft, and then of course we have the space-bound system like rockets and orbital depot and refueling. In this picture, you can see basically all the end user that right now are dealing with the liquid hydrogen from ground up to space. And we will see that a lot of activities right now is focused on concerning the liquid cryogenic storage. Is basically driven by spaceborne application, which entails additional challenge because, as we will see, the load, the life cycles is quite different and not directly applicable from the rocket application down to let's say an aircraft application. Concerning the ground installation, of course we are dealing with the let's say storage system which should have a very, let's say, lifetime about 20 years with hundreds or even thousands of loading, but normally they always maintain a liquid level, a minimum liquid level, in order to allow a chill down, to maintain the temperature and to avoid any, let's say, waste of liquid hydrogen during the cool down of the tanks. So they are always a little bit, there is always a, let's say, a minimum level below which is not recommended to go. And all the events of loading, unloading, all the gas is managed by use of venting or torches, flares in order to burn it. So the main requirements in this for this storage system is to cost not much normally and to minimize the boil off, in the sense that we have to minimize the losses that takes due to the thermal fluxes. So normally we are looking at very simple structures optimized to minimize the boil off. Normally cylindrical, or the best is of course is a spherical shape with different layers of insulation, normally vacuum, perlite or glass bubbles, which right now are the best solution to this application, and to reach a boil off of 0.1, let's say, percent in mass per day. And these are tanks which are, you can see the structure and the size are built in situ in place by standard welding application. So in terms of, we perform some calculation. I don't want too much into the details, but the idea is to say that that right now, in terms of effectiveness and cost effectiveness over the duration of 20 years, for example, a classical duration of this application, there is no, let's say, advanced material that can be, I mean, that is can replace a simple and cost-effective material such as, for example, stainless steel 316 or standard aluminum alloys in the class 5085. So considering all the code up, let's say the regulation for pressurized system, a cryogenic system, we see that right now we are in the state of the art in terms of this structure. So for application, ground application, there is no, let's say the margin of gain is very limited, almost nil. But when we go to application, let's say an automotive application, we will see that we will start to increase the complexity of the tanks. In this picture, we have, for example, a classical Daimler truck LH2 fueled system being developed right now. And we have, let's say, an increase in terms of requirements, which are linked to the use of liquid hydrogen. First of all, the safety. How we handle the boil off and all the accidental scenario. Cost of simplicity. We don't have to miss the fact that tanks that right now are normally cryogenic tanks for liquid storage are, let's say, in a niche market for heavy user, must be built at the production rate which is compatible with the automotive industry. And this is a challenge per se, because we have to build these tanks, the right quality in terms of safety and the thermal properties, but at the right production rate, and it's a challenge per se. So the classical solution that exists are vacuum insulated tanks, for example, developed by Linde, with a cylindrical shape, or even some more conformal shapes, due to the fact that we are working at relatively low pressures in order to fit within a car or a truck. So the boil off, once more, it shall be minimized in order to deal with safety issues, the constant release of hydrogen, and the autonomy for the truck. Then we step up in terms of complexity. The next application, which is right on track. There are quite a huge project in which we collaborate about the use of hydrogen in aircraft. So here I present some picture of a flown aircraft, one manned and one unmanned, which has been flown in the Soviet in 1988 by Russia, and a demonstrator for a long duration UAV by Boeing in the United States. So here we are increasing, of course, the requirements to the tanks in terms of life cycles, or in terms of duration, the number of cycles, of course, safety, because we have people on board. We have also increasing we have a larger dynamic loading in terms of stresses on the tanks for sloshing, the turbulence, the microgravity that can take place during the flight. Of course, the main requirement is to minimize the dry mass. So right now they are using non-structural tanks, meaning that the envelope doesn't support any stress from the environment except its own weight, with the stainless steel or aluminum lithium isogrid with the friction stir welding. And of course, we have once more the vacuum insulation for range of safety. This is basically the state of the art. And then the end of the spectrum in which all the development in terms of advanced materials are carried out is the space, the rocket system application. So, and we will see that all the development are carried out in terms of use of composites, CRFP, with or without liner, in order to minimize the dry mass in a rocket launcher, but the mission duration is very limited in terms of time, from 30 minutes, let's say, to 5 hours. There is just one use. There is a limited reuse, especially for an upper stage, and let's say the boil off, even the boil off, it's the specification for boil off is reduced, because once more we are dealing with the mission requirements, with the mission duration that is very short in terms of life cycles. So we are normally, people work with the metallic structures, aluminum, lithium, and with simple insulation, with glued sprayed foam from the external surface. There is no vacuum insulation with double wall vacuum insulation, and the boil off can be higher than 1% or even 2 or 3%, as we are constantly filling the tanks of the launcher up to the liftoff, and then the duration of the mission is such that there is no issue related to this boil off. As given also the fact that the boil off is reused for the attitude control of the launcher during the flight. So basically, in this slide, I present what the tank is supposed to do, because the material selection will be driven also by all the entire life cycle of the tank. The tank must be purged, it must be chilled down. Once more, we have to be sure that the desorption of chemical species that can be frozen in the hydrogen can be managed. We have to assure no leak tanks, so the use of liner or linerless tanks may be considered. We have to control the pressure in order to master how the liquid hydrogen is used. So we can have a fluctuation in the pressure inside the tanks, inside the tank, and also the use of pressurant, or basically hydrogen which has been heated by something else, which is constantly put on top on the tank. And this means that locally structure may have different temperature, and therefore we have to deal also with the low fatigue cycles due to these effects. Of course, metering, we have to meter what is inside, and also, of course, when we want to unload, we have to be very careful in considering cryopumping, basically the absorption of ambient air by the fact that surfaces are very cold, and this means that we can absorb and suck in air from the external environment. Then we have to deal also with safety aspects when let's say bad stuff happens. We can have the classical scenario of loss of vacuum, which means that we have to be very careful in the safety relief valves sizing. Normally, for standard application, these valves are close to the tank, but for automotive or even aircraft application, we can imagine that of having pipes, very long pipes, to evacuate the hydrogen in a different place, so we can have several meters of pipings, and this must be taken into account. We can have spillage and therefore ignition and collapse. The collapse is something that is very typical of cryogenic tanks. We do not manage properly the filling phase. We can have the collapse of the ullage, the vapor. Can be like in this example, can be condensed suddenly, and therefore the pressure inside the tank will be reduced with respect to the environment pressure, and we will have the buckling of the structure. Of course, we have a hydrogen embrittlement issue and a fatigue cycle associated with the loading and unloading. When we are dealing also with liquid hydrogen, we have the blaver risk, the fact that if we have a bonfire we can have the rupture of the tank and the sudden vaporization. We can have a lightning strike, so therefore we have to very carefully insulating the material, and then ground accident, whatever that can works. For example, we have a fire in the trucks, and we have to have access rapid access to the tank in order to vent. So looking at all the different application, this is very rapidly. I will explain this. Let's say the most challenging application right now that can drive the use of advanced material is the tanks for aircraft. Ground, as we said, there is a well-known let's say life cycle, and there is basically no issue, no margin for improvement, little margin for improvement. Automotive, of course, there are big issues, but in terms of mass reduction events, safety standards, and also safety rules, it's the aircraft that can drive tanks for aircraft that can drive the use of advanced materials. So what we are looking for is to have tanks with materials or with advanced material capable to minimize the dry mass. That's the first driver. With low density and high strength, of course, a good thermal performance at the low temperature in order to minimize the heat transfer. A good mechanical stability. We have to deal with the thermomechanical stresses induced by variation from 300 Kelvin ambient temperature down to 20, which this means that the expansion mismatch shall be minimized in order to avoid crack and delamination. We have to be resilient to defect. Chemical compatibility is not that much of an issue in terms of hydrogen with respect to the surface of the tank, but we can have, of course, a LOHC condensation, hydrogen condensation, sorry, liquid oxygen condensation on the other side. And of course, in terms of application, we cannot have a single event leading to a catastrophic failure and loss of life for an aircraft. Not to be forgotten, of course, that when we are looking at using hydrogen, we are storing hydrogen in volumes which have a more cylindrical shape. These volumes cannot be put inside the wings normally. So we are also losing. There is something that is missing, is the damping of the wings associated to the fluctuation, the load fluctuation. That's something that has to be taken into account. Of course, the manufacturability, inspection, and maintenance of these tanks is paramount. So in terms of requirement, we have to deal with the low thermal conductivity. I will go very briefly in this slide. The idea is to look for low thermal conductivity material to reduce the boil-off losses with matching thermal expansion coefficient. If you want to go for a liner, a tank with a liner, we normally use metals, and of course the compatibility in terms of expansion coefficient between the metals and the epoxies or let's say the carbon fiber materials has to be managed in order to avoid the lamination and infiltration of air, and of solidification within the matrix. We have to look also for high strength and low density. It's a criteria that is difficult to meet. Normally, alas, the best materials are also, in terms of strength, are also the ones that have a large density. So that's we have to deal with this. And also we have to look at the behavior under failure, because we have to be capable to master the propagation of failures, especially in an aircraft system. Fracture toughness and deformation behavior is the same. We have to look at how the structure will collapse in order to be capable to identify any failure mode before it occurs, in order to safe dispose of the hydrogen which is inside the tanks. So to complete very briefly, there are examples of cryogenic tanks with manufactured and tested with advanced materials. The first example is in the 1999, at the end of let's say the beginning of 2000, is Lockheed Martin tanks. They go for CRFP liquid hydrogen tanks for this single stage to orbit launcher. Alas, they maximize all the complexity. Basically, they went directly for a liquid hydrogen tank with a multi-lobe structure, with the load-bearing structure. Basically, the tanks has to sustain all the launch load with the shape which is not cylindrical, with no liner and a simple CFP. And of course, they had a huge delamination of the cores due to the cracking. So the fact that there was no liner led to micro cracks, which led to the accumulation of liquid hydrogen within the structure of the CFP panel. And then due to the heating, the pressure within the panel increased, and basically the structure of the tank exploded. So that's the first. Yeah, sorry.
Can you conclude in 2 minutes?
Yeah, of course. I'm almost there. More recent application are once more linerless application in 1986 that are flown, and right now the state of the art is something that has not been flown, is the use of a composite carbon composite structure with different laminations in order to reduce the permeability. They do not want to put a liner on it, but once more, these are rocket applications in which the permeation is not an issue. In Europe, the most advanced, let's say, activities are driven by the European LabCat collaboration with DLR and other institutions in which they develop, let's say, more common tanks. And I reach basically the conclusion that there is quite a lot of activity that has been carried out in the past and even right now. We can demonstrate a reduction using advanced materials by almost 30% in the tank structure, which is a good thing for especially for aircraft application. But the fact that we are developing this technology for rocket is mean that we cannot directly use it for airplane application or downgraded it to let's say automotive application for liquid hydrogen. So the mix, the path forward that we can let's say identify, we can foresee and encourage is to use let's say to separate the different functions, to use let's say to minimize the risk in terms to use the right material, let's say composite or advanced material for non-loaded structure with the warmer temperature, and then to use more standard approaches, for example, for when the cryogenic hydrogen is to be used. The challenges, and with this will be my conclusion, are first of all the manufacturing and the cost associated with it. The design policy, it's quite complex to design such system because the margin policy and the certification requirement are not known, and testing will be quite a huge challenge because we have to be able to test such system under realistic conditional loads. Represented from handling, flight, and also abnormal operation. And of course, we have to be capable to monitor the health of the tank throughout its operational life that could be ranged between 5 to 10 or 15 years. So the consideration is that a lot of stuff is already available, but what is to do is to think about the tank as a system per se, and to include the right material for with the right development logic for this application. Thank you to all, and if you have any question, I will gladly answer to all of you.
Thank you so much, Davide. It was a very dense overview. It's very helpful and very rich.
Absolutely.
I did not see any hands raised, and I did not see any questions in the chat, but you have an opportunity, all of you, to ask questions now. So I think we can take one question because of the time. And if there are questions that pop up later, you can still send them to us and we will give them to Davide.
Yeah, of course.
One question. I think that you said too much, so it's very clear now.
Yeah.
But you have a question.
Yes, Davide, this is Karim speaking. So I have a
Yeah.
So I understand that the main advanced material solution is for aircraft applications, right? And we see the same tendency as we are in the compressed hydrogen storage is to go towards composite materials, right? With development. Do you see any common development from compressed hydrogen storage world that can help the liquid hydrogen storage developments?
I think yes, of course we can have let's say an interaction between the compressed hydrogen. The issue is the temperature and the permeation of the molecule through the casing, let's say, depending of what type of tanks you have. If you can sustain 20K and all these issues, it will be a jackpot for us. I mean, we can reduce the risk by a common, let's say, use of fibers or material. But it's a little bit harder to work at low temperature due to all these material property issues. And also the cycles. The issue is the cycle. So we have to go to 300 to 20, and maybe from 20 to 300. And this is I don't know if you have the same delta T, the same temperature range in the compressed hydrogen.
Perfect. Thank you, Davide. Thank you for your presentation. We shift now to Earl Goetheer, who is going to present us ammonia.
Hello, I hope you can hear me.
We can.
Perfect. Let's share my screen one moment for it. So the next 20 minutes, 15 to 20 minutes, I'm going to talk to you about ammonia transport and storage for it. First, a couple of words about who is talking. My name is Earl Goetheer. I'm working as a CTO at a venture building company called Hydride XL. But I just started last week. Was my start of my new career. But before I worked as a principal scientist at TNO, which is the largest research organization in the Netherlands, and I was responsible for the main process technology. Next to my role as CTO, I'm also a professor at the Technical University of Delft at the Faculty of Mechanical Engineering for it. So with this, let's go into the field of ammonia. And before going to the future, I will always like to go a little bit back to the past, because ammonia has a big history, and without ammonia, we will not be with this moment in time 48 participants. Perhaps only half of the participants would be here, because we need it as a fertilizer, and without the fertilizers, we can't sustain 7 billion people on this globe for it. Now, in the past, options like guano was used, bird droppings, and transport via ships to Europe. But in around 1900, came the idea, let's go for bread from out of air, and that was really a major revolution when people realized that you can transform nitrogen from air into, in this case, was it nitrates, working with a plasma-based system. For it. You see the pictures now, so how they've done it in Norway around 1905, something like that. But then came Haber and Bosch. As a chemical engineer, these are basically almost like rock stars, because they developed the Haber-Bosch process for turning nitrogen and hydrogen into ammonia. And that's also the reason why we are now with 7 billion people. And if you look at your nitrogen atoms in your body, there's a great, big chance that these nitrogen atoms of your proteins, that they are coming out of a factory, because they're basically basically given to plants in the form of fertilizers, and we eat it and we turn it into our own proteins. For it. So large proportion of your proteins in your body comes, at least ammonia part, the nitrogen part comes from a factory. So that's the past, and this moment in time we are well above 170 million tons of ammonia for it, and this makes it one of the biggest commodity chemicals which we have for it. But it's as well responsible for a huge amount of CO2 for it. So a little bit not so nice, because we really need ammonia, because without ammonia we don't have the room to feed 7 billion people. But the consequence is a significant amount of CO2 is going into the air. For it. Now, if I just look now, where are we now with the current Haber-Bosch processes? They tend to be extremely large. For it. And the total efficiency of what will be around 60%, 65% for it. Scale 1,500 tons per day is a typical scale. It could be even larger for it. So this really large scale processing for it, and it basically also means that there's a complete transport infrastructure to transport ammonia all over the globe for it. Now, at this moment in time in Europe, because of the high natural gas prices, a lot of our ammonia plants are out or even turned down. But so that has some consequences for it. But let's move into where is this ammonia currently being produced. Now, look at this was a picture for 2020, so you could still see Russia there, okay. Nowadays we all know that it's not going to be supplying any ammonia to Europe for it. But if you look at the majority of the ammonia, for looking at countries like China and countries where you have cheap gas available, like Egypt or Saudi, and that's basically how it is, and then it will be transported to countries like within Europe for it. Now, if you look at a molecule like ammonia, often people say, yeah, that is dangerous and we have to be careful about it. Yeah, ammonia is a health hazard for it. If the concentration are too high, so if you are above, let's say 5,000 ppms for it, you basically suffocate within minutes for it. But there's one major advantage of a molecule like ammonia, is that you really smell it at very low concentrations. So already at 50 ppms, people smell it, and because you smell it, you can do an action like running away for it. So that's really one major advantage of ammonia. But ammonia is a dense gas, huh? So we have to be still careful with that. But overall, I already mentioned 170 million tons per year globally produced. So we know how to store it, we know how to transport it, and we can handle it at different scales everywhere on the globe. It has an acceptable safety history for almost 75 years. Of course, accidents will happen therefore. So be careful with that. Now, the thing is what is now really different is not now we're going into the energy transition. Basically, as a chemical engineer, I often say that the world which I know, which I've been trained in, is going to change dramatically. If you go to Antwerp or Ludwigshaven or Rotterdam, with the beautiful refineries and as well the ammonia plants, they will change dramatically because we want to do things now with renewable energy. For it. So, and that has a consequence for our ammonia demand. Basically, our current use of ammonia is basically fertilizers and feedstocks for chemicals for it. But we are going to move to additional things like ammonia as an energy carrier. So transporting energy from location one. So, for instance, in the Middle East, and transporting it here to the Netherlands and use it directly in a power plant, as example. and you turn in ammonia, so you go from power to ammonia to power again. The ammonia is produced in the Middle East, is brought here in Europe, and is cracked back to hydrogen. So then ammonia is a hydrogen carrier. Or another example of a future role of ammonia is that ammonia is used directly as a fuel. Think about not for planes, but for shipping, as an example. So as an, and that sounds very strange to say that, because we are not used to think like that. But the advantage of ammonia is that you basically can produce it everywhere. When you have cheap, abundant renewable electricity available, then you can produce hydrogen from it, and nitrogen, 80% in the air is nitrogen for it. So you can produce it in principle everywhere for it. Of course, it comes with a cost. Now, what is now key elements in it within this development towards this energy transition is that we're going away from gray hydrogen, which is typically working with methane, or in China with coal, to go to blue hydrogen, and then blue hydrogen can be used then for making blue ammonia, and basically then you store your CO2 under the ground. Then you have turquoise hydrogen. Basically, you take methane, you crack it to carbon and hydrogen, you couple this hydrogen to nitrogen, and you have your turquoise ammonia. And you, of course, you have green hydrogen just as well, and producing green ammonia for it. Now, if we look at the scenarios, where are we going to? I already said we are roughly at 170 million tons. And depending on the scenario you're going to take, if you look at a near net zero emission scenario in 2050, then we are talking about more than a factor of 2 increase of demand in nitrogen demand. For it. So it's a significant increase, and the majority of the increase is coming due to for other reasons than what we are having now. Think about indeed this is going back to power or using this as a fuel for it. So we need to think about what is the consequence now for the whole transport option, because the per location things will be different for it. So if as an example, let's look at Europe. This is coming from an IEA study. They predict in 2050 that the majority will be produced here with electrolyzers for it. Yeah, that's 2050. It's a little bit too far away from me, but if I just think about the next coming 10 years for it, Europe has said we are going to develop 10 megatons of hydrogen production, green hydrogen production in Europe, and 10 megatons of hydrogen will be produced elsewhere and will be transported to Europe. And a significant part of this 10 megatons, which will be produced outside Europe, will be coming in the form of ammonia for it. Now, why is there so much interest of having ammonia instead of exactly having hydrogen imported? Is because if you look at the energy density in kilowatt hours per liter, then you see an energy density of ammonia was significantly higher than, for instance, gaseous hydrogen in the form of compressed hydrogen. Or even significantly higher than liquid hydrogen for it. So this is much more easier to transport hydrogen in the form of ammonia or liquid organic hydrogen, which will come later on, than directly via hydrogen. And you can see it here as well in this picture. For it, which compares hydrogen transport either via ship or via pipeline, and compared with the cost of transport between ammonia via ship and pipeline. Of course, when you have a small distance, then pipeline is more advantageous, but ammonia can be perfectly transported via ship. For it. And if you look at the cost, just the transport cost, this is really a significant lower number than, for instance, transporting long distance hydrogen via ship. For it. Now, in general, this don't look please at the absolute numbers, because but just give the trends there. If you want to go for very large volumes and a very large distance, then transport of ammonia via shipping is more preferred than pipelines or liquid hydrogen or even liquid organic hydrogen carriers for it. So that's a rule of thumb for it. Now, how is now the cost of it? Because I showed you the cost of transport, but yeah, that's just transport. At the end of the day, if I want to go back to hydrogen, I have to do other things in it. So at first I have to produce ammonia. For it, and so I have to have hydrogen, and then I have to produce from this hydrogen. I have to produce ammonia, which leads to an efficiency of, let's say, 55%. So that comes with a cost. Shipping itself is typically a very low cost for it, and a third cost is then reconverting the cracking back of hydrogen back to cracking back of ammonia to hydrogen for it. Yeah, it's depending on the use case for it, but this is now for 2050, going from 2030 to 2050. And what you can see is that ammonia, liquid organic hydrogen carriers are way more cheaper as a way to transport, in this case, over a 10,000 kilometer distance than liquid hydrogen for it. So there's a clear options for using ammonia as a new vehicle for transporting ammonia as a hydrogen carrier over a long distance compared to other options. But okay, then we have to think about, yeah, good, we can produce that somewhere where you have a low cost related to green electricity. Then we have to think about how to store it for it. And of course, you have different options, and at the end of the day, it is really dependent on the scale of it. So if I go for the pressurized tanks or the insulated atmospheric vertical storage tanks for it, or the semi-refrigerated storage, they have all their benefits for it. And if you want to go for very large scale plants, very large scale storage options, then we're talking typically about quasi let's say 1 bar type of storage tanks for it. Please.
5 minutes?
Yeah, no worries. So typically around 1 bar storage tanks, which can store up to 5,000 tons in one of these units for it. But there's another possibility, and that's basically to store it into caverns. For it. And there are already 2 examples already known, one in the United States and one in Norway, with a scale of 20 to 50 kilotons for it. I think these are really one-offs, because one of the main issues when you store ammonia in the subsurface is the possible contaminations which you get when you extract it again from the subsurface. But in principle, you can store it for instance, in a salt cavern. You can store ammonia just the way in the same way as now store methane or even hydrogen in the subsurface. Okay, we know how to store it, then we can think about transporting it. Now, basically, 4 modes of transport: pipeline, rail, ship, and truck. If you look at the pipeline for it, we are already doing this over thousands and thousands of kilometers, not only in the United States and Russia, where they do this already on megaton scale. But even in Europe, we have capacities of Netherlands, for instance, of in total 4 kiloton per day for it. So that's really quite a substantial capacity. So we are already transporting ammonia for over quite some distances in the Netherlands. But if you look at typical lengths of it, and you see 10 kilometer, Italy 54 kilometers. Not in the same order of magnitude as in the United States or in Russia for it. Other possibilities to transport is via railway for it. Typically transport as a liquid at 15, 16 bars for it. The United States is a really very common way of transporting ammonia. But I think the most important for us in our discussion is transporting ammonia via ship. And typically, the ships which are using is used for ammonia transport are basically the same ships as for LPG. So only minor adjustments are needed to have this, because the conditions are quite similar, to be able to use it in an LPG carrier. Typically, the LPG carriers, we're looking at a little smaller scale, so let's say 20 to 60,000 cubic meter for it. Now, all this ammonia will come to certain locations, and you see now all over Europe, you see the ammonia terminals in the development for it, where ships can be docked. And there's an example in Rotterdam for it, where ships can dock their ammonia, can be cracked back to hydrogen, but can as well directly supply ammonia as in a gas phase for it. And these are connected to initiatives like in Norway, where they are producing blue ammonia. At least the desire is to produce blue ammonia and to transport it then back to locations like Rotterdam for it. But if you now look globally, because of all these interest in ammonia, you see a lot of these announcements related to new ammonia terminals for it. I hope that you've seen that ammonia is really an interesting way of transporting energy for it. We know how to do it. This last slide, that we know how to do it. And I personally think, just like this sheikh from Saudi Arabia, that we are moving to something better. Not because we have a lack of oil, but we also have something which is cheaper for that. So with that, that was my my talk, and I hope you found it interesting.
Thank you so much, Earl. Sorry for pressing you. We have time for one from the audience. I didn't see anything in the chat.
There is one on the chat. What the consequences will ammonia as a fuel have on the NOx emission?
Yeah, that's a hot topic, especially in the Netherlands and in Belgium as well for it. And of course, this will have a consequence for it. You can, of course, install an SCR, a selective catalytic reduction unit, because that works also well on ammonia, but it has a consequence. And that's really, in Netherlands, we, for people who don't know, we have a small issue with our NOx emissions and basically basically it throws a spanner in the work of many of our companies. They don't get permits, but indeed ammonia as a fuel, as a shipping fuel, will lead, if you don't design it well enough, lead to higher NOx emissions. But if you use an SCR system, you can really combat that. I hope that's an answer to your question, Erwin.
Thank you, Earl. I just had also one question. I read a lot about the toxicity of ammonia to ecosystems in case of leaks. Is this well documented now, or?
The toxicity of ammonia in case of leaks?
In case of leaks in the marine environment.
Yeah. So there has been studies now done, and even a study looking at what will happen if such an ammonia ship will sink. Yes. Because ammonia is very toxic, and you basically sterilize the whole sea around it, because all the fish will die. For it. Fortunately, it is broken down again. So it's not that persistent, but there are quite some studies now available on the safety aspects of ammonia, and we're already doing this for 100 years or roughly. So there's quite a lot of knowledge has been built up related to the safety aspect.
Okay, thank you. One last question from my colleague Ton at UMICORE.
Yeah, thanks for your contribution. You're mentioning using ammonia direct as fuel. Do you know the composition of the exhaust gas of an ammonia combustion engine, and then especially with respect to laughing gas formation? Do you have information on that?
No, Tom, I am now going to speculate too much, so I can send you some information on that via the email, but otherwise it will be too much speculation. Okay. Thanks a lot.
I'm happy I could.
Okay.
Thank you.
We would take a small coffee or biological break, and I would propose that we start in 7 minutes, if this is time enough to pick a cup of coffee. And so at 11:35 we start again, and then we will go over the next technologies. Thank you so much.
Thank you. Okay, we are all back. Next presentation is with Felix Heubner, and he will explain us what advanced materials do in hydrides and solvents.
Now you can hear me. Hello again. Hello, Marcel. Thank you for introduction. I hope you made your way to the coffee machine in 3 to 5 minutes. And you can see my screen right now. Yeah. Okay, thank you. So yeah, my name is Felix Heubner. I'm from FRAUNHOFER IFAM in Dresden, Germany. I'm leading here a small group of scientists that is related to research in the field of hydrogen storage in metal hydrides and the combination in energy systems with fuel cells, for example. The FRAUNHOFER IFAM is an institute called Institute for Manufacturing Technology and Advanced Materials. We are roughly 700 people. 100 people are sitting in Dresden roughly, and all the hydrogen related topics are operated in Dresden as well. Yeah, in terms of metal hydrides, or in a more general naming, hydrides and sorbents, that's a group of materials that is able to interact with hydrogen in form of an adsorption of the on the surface, for example. These can be metal organic frameworks, for example, or even carbon-based materials. Second group is the group of metal hydrides, or not only metal hydrides, so let's call them hydrides and complex hydrides. This is a reaction that happens inside the material, so it's an absorption process. And we can see, maybe when we only have a look at the volumetric capacity of these materials, that they can store up to 150 gram hydrogen per liter. This is even more compared to 700 bar gas storage or even liquid hydrogen storage, because hydrogen is bound inside the crystal lattice, for example. And that's one of the very main advantages of this sorbent storage. The gas pressure for the hydride formation is very different for the different hydrides. For metallic hydrides, we have often gas pressures between 1 and 30 bar. For temperature ranges, let's say -10 to 100 degrees Celsius. So there's always a relation between temperature and gas pressure, because we have this chemical reaction in the background. To just name one example, more specifically now, that's can be magnesium that reacts with hydrogen in the gas phase to magnesium hydride. Can you see on this slide? The reaction takes place at 300 degrees Celsius, for example, and 5 bar hydrogen gas pressure. The formation of a metal hydride in terms of the chemical reaction is an exothermic reaction. So heat is released during formation of the hydride. And when you want to decompose the hydride to release hydrogen to your fuel cell, for example, you have to deliver some heat from the fuel cell, for example. So you have to provide energy from the usage, for example, or the utilization. Metal hydrides or sorbent storage have the main advantage that hydrogen is bound to the materials. So on the one hand side, it is a very safe storage way, because hydrogen is not only available in the gas phase and can be released during a leakage at once. Hydrogen is bound on the materials, and so it's a more safe storage. And in combination with the boundary conditions in terms of temperature and gas pressure, can be even more safer, because you have only low gas pressures often available at medium temperature ranges. So the hydride diversity is very, very huge. So a lot of materials absorb hydrogen or adsorb hydrogen on the surface. These are just some examples about interstitial hydrides, so metallic hydrides that are very cycle stable, for example, can be cycled a few thousand times. This can be titanium manganese based hydrides like this ones here, or titanium iron based hydrides. So I already told you that temperature and gas pressure is always different for the different hydrides. And this is what the graph here on the right-hand side shows you. It is the temperature of operation and the gas pressure for the different materials. We have here one example, this titanium manganese-based hydrides. Behind this curve, that's a Fraunhofer plot here, behind this curve stands a pressure composition temperature diagram. And there are different values for absorption and desorption available. So we have more like a corridor for each material, not only a straight line. So this is titanium manganese based. We have some complex hydrides available that have a higher gravimetric storage density, for example, like sodium aluminum hydride here, over here, or some magnesium nickel based hydride, or even pure magnesium hydride operating at higher temperatures. The metal hydride family is having often a very, very high volumetric storage density, but you need always the host metal to carry the hydrides. Means that the gravimetric storage density is sometimes low, so these conventional interstitial hydrides are not used for mobile applications. They are more used for stationary applications, and there's a lot of research going on in the field of complex hydrides. And this is just one diagram from a review where you can see different complex hydrides like lithium boron hydride, for example, that can host up to 18 mass% hydrogen inside, and having the same time a very high volumetric storage density, again, of above 100 gram hydrogen per liter, so roughly ×3 compared to liquid hydrogen. In terms of applications and commercial operations of these hydrogen carriers in the past years, there's a very a popular one of the that's a good example maybe coming from a German company. It's ThyssenKrupp Marine System. A German submarine is running with a fuel cell and metal hydride storage on board, and ThyssenKrupp is using here that the desorption of hydrogen is endothermic, and you're having heat released from the fuel cell, so you can use the metal hydride storage as a heat sink here for this marine application, for example. The interstitial hydrides are used for materials handling devices as well, and here from GKN, for example, for a stationary storage system, there are smaller mobile applications like some kind of scooters here as well, published a few months ago. You can use hydrides not only for storage, you can use them for compression, for example, as well, because you have the relation between temperature and gas pressure, what is very interesting. So you can use hydrides for building thermochemical compression systems for hydrogen. Yeah, again, combining this thought about reaction enthalpy. So absorption is exothermic, desorption is endothermic. You need always, for a hydride application, a heat source available. So every material needs to be integrated into an energy system because you need waste heat. That's just one example of a fuel cell, a very schematic drawing here, having a fuel cell in operation on the left-hand side, fueled from a hydride storage. Heat needs to be transferred to the hydride storage to release hydrogen again. So it is possible to, let's say, integrate 1/3 of the exhaust heat of a fuel cell to the hydride storage to release hydrogen here. To sum up the advantages of the materials, you have a very high volumetric storage capacity, in theory, by up to 150 gram hydrogen per liter, and a low working gas pressure at the same time. Hydrogen is bound to the materials, so you have a high safety of these materials. There are some disadvantages. Of course, you have a low gravimetric hydrogen storage capacity because you need the host material first. The thermoconductivity is often limited of metallic or of powdery materials because you have small particle sizes, so dynamic operation is limited. And you have a volume expansion of the materials during hydrogen uptake. And I want to show you this radiograph sequence of a granule of 1 centimeter diameter, like it's absorbing hydrogen. So now it already absorbed hydrogen in a few seconds. And from this granule results a powder bed after only 1 cycle, because this was a very brittle material here. It was titanium manganese based. And after 1 cycle, we had fragments between 100 micrometer and 1.5 millimeters. So this is something needs to be taken into account when one is designing a storage system based on hydrides, for example. All these points here: slow thermal conductivity, volume expansion, decapitation upon cycling. This is these particles becoming finer and finer during cycling, are terms that are elaborated in R&D project the last years. So one solution is using metal hydride composite materials. I will skip this slide here. The composite materials use maybe the basis that is possible to add to a metallic powder or to a powder that is able to absorb hydrogen. A second phase is needed to increase the thermal conductivity of the powdery material of the first one. So both materials are mixed, blended together, and compacted afterwards in a uniaxial press to such kind of a tablet. And these tablets have now increased thermal conductivity of, let's say, 5 to 100 meter in Kelvin, and a reduced porosity of the powder as well. So it's easier to integrate these kind of tablets into tube bundle reactors that are made to store hydrogen. So the tablets have, when we have a look at the cross section of these materials, an anisotropic thermal conductivity, because the materials inside sometimes align in radial direction. So that's nice for heat transport in radial direction to the outer wall of the pressure vessel. So how to integrate these materials? When we have tablets, we can think of some kind of cylindric design of a storage vessel. Can be a tube bundle reactor as well. So easy scaling by parallelizing one pipe with following pipes. Inside this storage vessel, we have the compact materials, for example, these materials with higher thermal conductivity. And there's some free volume reserved for the volume expansion of the materials. So always taking into account heat management inside the materials bed here on the right-hand side. So transporting heat to the place of reaction and releasing heat when it is needed. Yeah, this is how it could look like in prototypes. This is a very simple design here, tube bundles design. The pipes are made of 316L, so good chromium nickel, austenitic stainless steel that was used here for the storage system. Maximum pressure was, let's say, 30 bar hydrogen gas pressure. It was made to operate next to a stationary PEM fuel cell using exhaust heat from the open cathodic fuel cell system, and integrated here afterwards over the outer walls of the pressure vessels. These composite materials are made in uniaxial presses that are known in the powder metallurgic industry for several years. They were used in the past for producing gear parts, for example. It's one very famous example. So these machinery can be used for producing composite materials in terms of hydrogen storage here as well. Just to show you one example about the dynamics of a titanium manganese based material during hydrogen absorption and desorption. Here on the left-hand side of this slide, you can see the temperature of the experiment versus time. And here on the upper part, the pressure in black and in the volume in the red curve. So pressure is increasing for refueling of the materials, so loading the materials above some kind of an equilibrium pressure where the hydride formation takes place. This was here something like maybe 20 bars, so we increased pressure until 40 bar. We see the exothermic absorption of hydrogen. We have a good thermal conductivity, so low gradient inside the materials. And most of the absorption took place in 250 seconds. So after a few minutes, the materials were fully filled here with hydrogen. The desorption is then at a constant temperature, triggered again from the gas pressure. So only lowering the gas pressure will lead to decomposition of the hydride. And we see here the endothermic behavior of the materials. So there's a volume expansion going along with hydrogen uptake and shrinking during desorption of hydrogen. So the materials need to be stable during cycling in such a pressure vessel. And that's one example of the materials after, I think, 40 to 50 cycles here, the materials remain stable inside. So I want to show you again radiograph series of materials that are absorbing and desorbing hydrogen in a cyclic behavior. And it's a neutron radiograph series. So the darker the radiograph is in the area, there's more hydrogen because you have a high interaction between neutrons and hydrogen. So black means hydrogenated state, gray means dehydrogenated. And I'm starting right now. This is hydrogen absorbing material on the left, on the middle, and on the right. And it's absorbing now in a few seconds and desorbing again in a few seconds. And you can see, for example, the volume expansion during absorption and shrinking during desorption. And the darker regions are highly hydrogen filled here in this case. And the light gray regions show you the dehydrogenated states. So that's something when we think about the materials and the energy systems and how to integrate these materials into storage vessels, it's always very important to have a look at this intersect or at this boundary condition, volume expansion, pressure vessel design, for example, from a chemical engineering perspective. Yeah, R&D in the field of sorbents starts often with evaluating application scenarios because you need to think the storage materials together with exhaust heat. It follows with a fine-tuning of materials, for example, to fine-tune gas pressure and temperature where the hydride formation takes place. Follows via synthesis and analysis, end-of-life recycling concepts. Integration into energy systems with simulation and modeling, for example, and engineering prototypes going the whole way around. To sum up this talk and give maybe some outlook about future perspectives in terms of R&D and materials. A lot of materials absorb or adsorb hydrogen at low gas pressures, but it's very important to understand this chemical reaction. So heat needs to be used for desorption of hydrogen, for example. One of the main benefits is the enormous volumetric storage density. It's up to 95 gram hydrogen per liter for very common alloys that are cycle stable, can be even higher for complex materials, up to 150 gram hydrogen per liter, so factor 3 compared to 700 bar gas storage, for example, on the level of the material. Yeah. The reactions are safe because the hydrogen is bound on the materials to have this link to safety again. And R&D is performed these days in terms of cost because cost of the materials needs to come down. Sometimes there are materials inside for catalyzing the reaction like vanadium, but there are some very low cost materials available like iron, titanium based alloys, for example, or manganese-based alloys. So this is very important to lower the costs here on a system level. Having a look at the same time on kinetics, cycle stability, storage capacity. For not only for storage, but again for compression, and there can be other applications like purification of hydrogen using metal hydrides, because this reaction of hydride formation is a selective reaction. So when you have a gas mixture of hydrogen, nitrogen, for example, you can use the sorbents to grab hydrogen out from the gas phase. And then we need fine-tuning of the alloys for the different fields of applications, for example, storage, compression, purification, and so on. Yeah, integration into energy systems is needed. Thermal management is important. Composite materials might be a solution. And one should look at the volume expansion and swelling. There are some standards available that are focusing here on this point. Very interesting field of research, like aging and filling level indication for monitoring of the materials, because measuring the filling level of sorbents not so easy. For a gas pressure storage device, you cannot only use measuring the pressure of the storage system. You have to take into account the temperature as well, and maybe the history of the materials. That's it. Thank you very much for your attention, and I'm not sure if there are any questions in the chat right now.
Thank you so much. There is one question for you in the chat that I leave it up to Marcel to read.
Okay.
This one, what is the technology readiness level of the main hydrides and sorbent system? So what TRL level are we talking about?
It's very different depending on the area or the family of materials we choose. So there are very basic TRL R&D going on to increase gravimetric storage density, for example, with boron-based hydrides. But all these interstitial hydrides, for example, are approaching a very high TRL right now, especially with the demonstration from GKN last year. So having maybe TRL 7 to 8 in operation next to a chemical plant applying exhaust heat. Yes, so depends. Material 3 to 7, and the storage systems that are in operation 7 to 8.
Don't see any other question.
Yes, there is a question from Ton Janssens at UMICORE.
Yeah. So you say that you're using your metal hydride because of the material properties, it's expanding and so on, and bad heat transfer with a thermal conductor material, typically a metal, I understand. But then you're also reporting hydrogen storage capacities per liter. So does that include this additional metal, or is that only for the hydride phase?
That's for the hydride phase. So these maximum volumes, values up to 150 are just focusing on the materials. When we're talking about storage densities on a system level, we have to take into account that there's a porosity, maybe, that there's a second phase available. So these, let's say 150 are lowered down to 75 to 60 gram hydrogen per liter, including porosity, second phase, and the pressure vessel around it.
So roughly, so if you take the material, the capacity of the material, we have to take, say, 30 to 40% of that to a technical application of that value.
Let's say 50%.
Okay.
Over the thumb. So having the half maybe in the storage system.
Okay, thank you.
There's another question from Schumacher. Gert?
Yeah, thank you, Marcel. And thank you, Felix, for this nice presentation. My question is, I followed up on this research like 20 years ago, and the main problem, it was like work from Professor Bormann and Canadians, was the kinetics. That was always the problem, that the desorption would be too slow. So has there been a breakthrough lately? Could you say something about that? Thank you.
It's, again, not easy to answer. Depends on the materials that are used. So for some materials, kinetics are a problem. This is the low TRL materials, maybe in such a saying. And there are a few materials available, like these titanium manganese-based alloys, that can absorb hydrogen in a few seconds when there's no heat transport limitation. So in terms of reaction speed on a system level, it's very important to think on transferring the heat inside the material's bed, so inside the pressure vessel, and transferring the heat from the outer surface of the pressure vessel to the ambient or to the heat source. So when these both points are included into the system design and engineering, the kinetics are not limiting today.
So
Thank you.
that will conclude your intervention, Felix. Thank you again very much. It was really a materials presentation.
Sorry for that.
That's very good. Now we go to Tom. Tom, please. You are going to present us liquid organic hydrogen carriers. Tom,
Yes.
is it working?
Sharing your slides?
So yes. All right.
Yeah, it works.
Yeah, there.
Yes. Okay. So now it works. So yeah, the next one is on hydrogen storage in liquid organic hydrogen carriers. It has been already mentioned in previous presentations. So let's start out with it. What is the principle of the idea? So it is we use organic molecules to store hydrogen. Yeah, and as an example, on the screen down here, you see these aromatic molecules that are capable of reacting with hydrogen, and then you can release the hydrogen again. So that means we are going to make a cycle where we start with some kind of energy source to create electricity and then produce hydrogen by electrolysis typically. We have a reactor to hydrogenate the molecule, and then you have the hydrogenated molecule which you can transport and store over large distances and keep for a long time. And then you put it in the dehydrogenation part where you release the hydrogen when you need it. And then the reaction product is then the hydrogen. And then we are back to the original molecule.
What?
Yes?
Your slides are not moving.
And we
My
put
slides
them
are not showing.
No, they are not
Moving.
moving. We are still on the first slide.
You are still on the first slide. Okay, that is yours. That is okay. Let me try to do it this way then. Can you see the second slide now?
No, we don't see
You
anything.
stopped sharing.
Okay, so and this is so let's go back to the meeting. Share screen. You see the slide now?
Yes, but put them in full screen, but maybe.
I am in full screen. Is
We only see partly the slide, not totally.
yeah, that so
Could you be in the presenter mode, please?
I am in the presenter mode.
Yeah, but we see.
Ah, okay, that's not what you see. Okay, like this?
Oh, no, it's not working. Maybe Marcel can share the screen and you tell us when you want to change the slides.
So resume slideshow. I mean, this is all what I can do.
Tom, if this is okay for you, Marcel. Marcel is gonna. Marcel has your slides, I think, so he can share your slides. And then
Okay.
you want us to change the slides for you.
I don't have the slides.
Oh, you don't have the slides.
No.
I can send the slides immediately.
I think you can say like this, but when you need to change the slide, just click on the second slide on the left.
Yeah. Here.
Click on this. Click there.
And then you.
So I don't know what you are seeing. That is my problem.
Your first slide, your
What do you see now?
The blue slide, the introduction slide you see.
This is, I mean, so this is, all right. Where's my mouse? This is incredible because this is exactly what we tested before. So F5. But all right.
If it doesn't work, send me your slides.
Yeah, I am.
Okay.
This is feasible, you know.
Okay, I think we see better like this.
Yeah.
Can you scroll to the next slide?
Yeah.
Yeah, it works now.
Yeah, yeah, it works. You're on the second slide now.
Let's do like this. Just scroll down when you want to move from slide to slide.
Okay, Ton, we hear you. But Ton
is connected to the audio.
So
Ton, I propose you send me your slides and I will scroll them for you. And
yeah, I understand, but there is a big confusion about. Can you see something now?
Now it's great, yeah.
What?
Yeah. This is excellent.
Perfect.
This is excellent. Okay.
but now you have removed the screen again.
I took it away.
It was okay, but you stopped sharing.
What is this? It's throwing me out all the time. Screen one. Allow.
Yeah, okay.
Okay, we see the slides now.
All right. Does it work?
This works.
Perfect.
All right. Sorry for the technical things. There is a big confusion between the web browser and the PowerPoint. Okay. As I was saying, we are completing the cycle, and at the end of the cycle, so with the after the hydrogenation and dehydrogenation, we end up with the same molecule, so it can be in principle reused indefinitely. There are many liquids that you can use. So liquid organic hydrogen carriers, these are normal organic molecules. I want to exclude in this point the molecules that will produce a gaseous product as well. And this is also where ammonia comes in. So this is different from what we heard in the ammonia concept before. So the attractive features of using an LOHC, it is very easy handling. I mean, it's just oil like diesel. So the hydrogen is stored in there in a quite high amounts. And because this is an oil which is further fairly stable and not reactive, you can use existing oil infrastructure. And this is tankers, pipelines, pumps, and whatever. It's not different. So the typical compounds for aromatic compounds, these are toluene, 2-methyl cyclohexene, or benzyl toluene, fairly simple molecules. And there's also a technology available that uses heteroatomic compounds, which is pyridine, piperidine. They have an advantage. They are have a little bit lower reaction temperatures. These are normal oils, so it is actually a really safe storage. So hydrogen is not stored as hydrogen molecule, but it is released from the oil on demand. And then another attractive feature of this technology is that in principle, all parts of what we need to do are very well known. Yeah, so hydrocarbons, they are available in large amounts. We don't need new materials for that. Catalysts are known how to do it, and so on. So basically, on the technical side, we are pretty much ready to go on that one. So we have seen a couple of slides already on how the technology compares to alternatives. So I basically want to focus here on the volumetric energy density of the system. With an LOHC, typical LOHC, we do better than with liquid hydrogen. We're not quite as high as on ammonia. And if you compare to conventional fuels like diesel, we are like at least a factor 2 to 3 lower, and that also goes for ammonia. So that means, as a consequence for transportation, you need to move around larger amounts of this LOHC as compared to diesel. Yeah, so also for pipelines, the energy density in the pipeline will not be as high as we are used to from oil. If we compare to hydrogen storage materials, of which we had a nice presentation just before, typical hydrogen storage, effective hydrogen storage capacity in an LOHC is 4 to 5 weight%. And the temperature you need to release the hydrogen is typically between 230 to 280 degrees, sometimes a little bit higher, with the pyridines a little bit lower. So we are operating in this box that is in the graph. So we are comparable to a lot of hydrides, but temperature will always be an issue. And then about the safety. So this is kind of a gimmick experiment where you try to ignite hydrogen stored in an LOHC. So as you see here in the picture, it's a liquid, and you can basically throw a flame on it. You can see the video on YouTube where they actually put a Bunsen, a gas burner, directly on the liquid, and nothing happens. It's essentially a diesel oil, so it's very difficult to ignite. So to release the hydrogen, we need a catalyst, and catalysts are actually well known. These are dehydrogenation reactions, and noble metals are so supported. Noble metals like platinum, palladium, ruthenium, rhodium are will work with for this reaction. So to make a catalyst, you start off with a solution of a salt, of a platinum salt, which you impregnate on the support material. And I think the spheres here is actually a high surface area alumina. You dry them, heat them, calcine them at about 400 to 500 degrees. Then they turn black. And the black is because of the metal particles. So in case of platinum, the heating will lead to formation of some metal, and with the metal oxide outside on it. And you can see in the sphere, so the platinum will typically be located at the outside of the spheres, which is good because that ensures good contact to the oil. These are just some examples showing that you can actually use different catalysts, and this is actually for the hydrogenation. Yeah? The hydrogenation and dehydrogenation catalysts are essentially the same materials. So for ruthenium and the rhodium, you see at 180 degrees in the left graph, they work quite well. Platinum is actually the most active one, and then palladium in the right graph. And a nice illustration of why you would use different metals is that palladium, it's not as active, but it can tolerate some carbon monoxide in the gas, and platinum just doesn't work. These are the circles in the bottom show that if there is high carbon monoxide present in the gas, the platinum doesn't work anymore. So this is a little bit the space we are moving in, dependent on the process conditions that we have. You select a material. Platinum is also good for dehydrogenation. The difference between hydrogenation and dehydrogenation is that the dehydrogenation typically takes place at a slightly higher temperature. So that is around 250 degrees, and you lower the pressure. So hydrogenation is running at 20, 30, 40 bar, and dehydrogenation is essentially running at atmospheric pressure, or maybe up to 5 bar. So that is how you can tune your LOHC process cycle. Then another point is that to have enough catalyst activity, we want to have small particles. And we are actually aiming for particles that are about 2, 3, 4 nanometers in size. There is another point to be considered, and that is that there may be unwanted side reactions. So the reaction is running quite well. The liquid is very stable, but during the reaction, you may find that some of the hydrocarbon molecules break, and then they typically will produce heavier molecules, which have a higher boiling point. So this is what the high boiler formation refers to. And if that happens too much, then of course your liquid is not stable. It will have a limitation in the application, and you want to prevent that. And in the graph to the right, you see that the high boiler formation is very much dependent on the platinum particle diameter. So this is also something we have to compromise. So we want to have very small particles for the activity, but we don't want the oil to break too much. So for platinum, this turns out to be an optimal particle size of around 3 nanometers on the support. So far so good. But there is also a problem, and that is the thermodynamics. It has already been mentioned before. To store the hydrogen in the molecule, we have an energy release of about 65 kilojoule per mole. And to release it, so in the application, we have to provide this 65 kilojoule per mole. And 65 kilojoule per mole is 27% of the combustion energy of hydrogen. So it essentially means that we need to that we actually lose about 30% of the energy content in the hydrogen that we want to use, just to keep that reaction going. And this is a major factor that actually limits the efficiency of the process, and it's also the reason why the useful hydrogen storage capacity is around 4% and not at the theoretical 6.5% or so. Yeah, so to do LOHC, you have this cycle where you have the hydrogenation, and then you have the hydrogen-rich LOHC. And with this hydrogen-rich LOHC, it's a stable molecule, it's oil. Yeah, you can transport it over long distances and so on. And once you use it for dehydrogenation, I have drawn this here, you get your hydrogen out, but you have to use a part of the hydrogen to keep the dehydrogenation reaction going. Yeah, it's essentially the same problem as with ammonia and also with the solid hydrogen storage materials. So a solution to that is just to install a burner to heat the reactor. and use a part of the hydrogen that you have released to keep the reactor warm. There's also other solution. You could also think of electrical heating, and if you have combined it with the fuel cell, this is an engineering part. Then the difference also with ammonia is there is a return line. So you end up with the dehydrogenated oil, and that has to be returned to the hydrogenation. So if there is a few thousand kilometers in between, you have to transport it back. If you use a pipeline, you also have to have a pipeline that goes back to the reactor. And that is, of course, a system that, you have to think about how to do that, and it's part of the technology. So then a few words on what you could imagine. So this is an estimate of the annual demand of LOHC, and of hydrogen, and then an estimate on what LOHC could do. So I think the take-home message from this is that LOHC is really at the beginning. So it will be at least 10 years before it gets some volume, and that it's expected, if this is going to fly, that is on 25 to 30 years. But with these volumes, the other interesting part I want to draw attention to is it will require a certain amount of platinum. And the numbers we estimate is from what we have measured in the lab, how much hydrogen how much platinum we need to produce a certain amount of hydrogen. And from that estimate, we come, if the technology grows to this level, that we need 30 to 40 tons of platinum per year. And that has to be seen in perspective of the total platinum production, which currently is 200 tons per year. So in that sense, this technology is potentially a large fraction of the noble metal usage in the world. And then the application. So I think the current vision for LOHC is to transport hydrogen over larger distances. It's a little bit the same as with the ammonia. And so the idea is to do this, to hydrogenate at the production site of the hydrogen, keep it in the oil, and then transport the oil around the world where the hydrogen application is located, and then dehydrogenate there. So it will so typical application will be, for example, take it on a ship, put it in the harbor, and the harbor has a dehydrogenation plant where it's fed into a hydrogen net, for example. If you look at the cost of these kinds of operation, then in the graph to the right, we see a comparison of the cost of ammonia and liquefied hydrogen and LOHC. And we have seen a similar one. So the cost of this operation is very comparable to that of ammonia, but it's clearly cheaper than handling of liquid hydrogen. So in conclusion, I say that LOHC has a useful hydrogen storage capacity. 4 to 5% is very reasonable. We reach an energy density that is somewhat lower, or a bit lower than in current fossil fuels, but it's useful. With LOHC, you can have an effective and safe transport of hydrogen. And another positive point is that all required materials, catalysts, are actually known today. So we basically can put it together today. All process steps are known. And last but not least, the LOHC compounds. These are in principle oils that are used in heat exchangers today. They are widely available today already on a commercial scale. So then a little bit to the lesser points. The technology will require quite a bit of logistics. We have to figure out how you return the used oil back to the hydrogenation plant. And if you put it on a vehicle or on a ship, you have to think about the tank system, because you have to retain the used oil in one way or another. About cost, it seems cost competitive. And the last point is that engineering of the heat management is a challenge for this technology. It is very much like the points for ammonia and solid hydrogen storage materials. So I thank you for your attention, and sorry about the technology that failed.
No problem. Thank you, Tom. Other questions?
Yes, there's a question of Rosalina Perez. You raised your hand, Rosalina.
Rosalina?
Rosalina is gone.
No, she unraised her hand.
Okay.
Maybe I have one, Tom. What about the toxicity of those oils? Is everything okay there, or can the thing?
It is, yeah, it is compared to ammonia, it's much better. Yeah, I mean it's also a liquid, yeah, so it doesn't spread that much. These aromatic oils, it's yeah, say compare it to diesel oil, so basically conventional oil that we are using today. So it's not healthy to eat, but very manageable for us.
It's a good gastronomical comparison.
Yeah.
I have a last question from my side. It's how do you compare methanol and LOHC?
Yeah, I have I've done that. I've excluded it here because if you use methanol, then you end up with gaseous products again. Yeah, so it's not the liquid carrier as such. Yeah, you're going to produce methanol from basically CO2 and hydrogen, and then on the usage of methanol as a hydrogen source, you are producing CO2 again. So it is in that sense, I would not call it the LOHC cycle. It's then more like ammonia. Energy density is better with methanol than with these molecules.
Thank you, Ton.
Maybe the last question here from Luca. Is there any limit in terms of scaling down of the technology? Thinking for storage?
Yeah. I think at the end it's the cost, and you still have to run a reactor somehow, and I think that is going to be the limit. You have to put in heat the reactor. You have to have the extra heat in all the time. Yeah, so you could also imagine, yeah, if you make a system where you add an extra solar panel to heat the reactor, then it could possibly be done. Yeah. Then the question is, does it make sense to transport hydrogen that way? Yeah? And because you have to put in the energy twice. Technically, you could make a small reactor. That wouldn't be an issue.
Okay, very good. Thank you, Tom, again. And then we come to the last presentation, which is about pipelines. Please, Tom, we are listening to you.
I think you should be able to see the screen and to hear me.
Yes, we can.
Okay, very good. Hello, my name is Ton Depover. I'm a part-time assistant professor and postdoctoral fellow at Ghent University, and today I will present the results of a review performed on the evaluation of using the existing pipeline natural gas network for gaseous hydrogen transport. So an overview of relevant factors affecting the material degradation by hydrogen will be discussed. And this work was a collaboration between the Sustainable Materials Science Research Group and Sute Laboratory, represented by the co-authors of this presentation. The European Green Deal states that Europe has the ambition to become the first climate neutral continent by 2050. Using clean hydrogen gas as an energy carrier in this renewed energy landscape seems very promising. I will focus today on the challenge of finding an efficient logistics system for hydrogen storage and transport, essential for the successful implementation of hydrogen as an energy carrier. A timely transition to a sustainable energy-based economy requires to incorporate the existing natural gas infrastructure into the hydrogen logistics, as shown here on the left-hand side with the European hydrogen backbone. However, atomic hydrogen can enter a microstructure of steel or other metal by dissociation of hydrogen molecules or by reduction of protons, for instance, in the case of cathodic overprotection. And this can lead to hydrogen embrittlement. This hydrogen embrittlement causes a variety of degradation modes in otherwise high-performance steels. Hydrogen is known to potentially increase the growth rate of existing cracks under cyclic pressure, deteriorate the fracture toughness, and also give rise to hydrogen-induced cracking when severe charging is applied. For instance, in this case, in this picture, you can see an X70 pipeline steel where cracks were initiated in the hard segregation bands showing MNS inclusions and niobium-based carbon nitrides. This is the content of my presentation. I will start generally on hydrogen embrittlement of pipeline steels, and then we will talk a bit more about different influences. Well, we have two different types of testing. We have quasi-static testing, where the quasi-static load refers to a load which is constant in time or changes very slowly. Quasi-static loads in pipeline steels originates from gas pressure of the transported gas or internal residual stresses in the material. Cyclic loading then is more associated with fluctuations in the gas pressure and applied loads on the pipeline structure when used to transport or store pressurized hydrogen gas. The resistance of a material against quasi-static load is described by its mechanical properties. For instance, tensile properties, yield strength, tensile strength, ductility, and also fracture resistance properties like fracture toughness. The ductility of pipeline steel, which is typically expressed in terms of reduction of area at fracture or elongation to fracture, is significantly reduced in the presence of hydrogen. For instance, hydrogen can reduce ductility of smooth specimens and fracture toughness up to 50%. A standard cup and cone fracture features, they turn towards a reduced necking, as you can see in the microscopy pictures, and poor ductility in the presence of hydrogen. Well, this was with quasi-static. Let's go to the cyclic loading. Well, hydrogen-assisted fatigue crack growth takes place under cyclic loading, and this is considered to be the main mechanism of hydrogen degradation in pipeline steels transporting hydrogen gas. Hydrogen can drastically increase the fatigue crack growth rate up to 2 orders of magnitude, according to the literature. This fatigue crack growth rate test method is more appropriate for evaluation of the fatigue behavior of pipeline systems, as the method assumes a pre-existing crack. This is in line with the fact that welds, for instance, contain small imperfections, and these imperfections, they can serve as a crack initiation site. The exact influence is determined by many factors, many parameters, such as the material, the microstructure, the load frequency, the stress ratio, the hydrogen gas purity, and pressure. The figure, for instance, shows a typical fatigue crack growth results that are obtained from fatigue testing in a gaseous environment, where you can see an increased crack growth rate in the presence of hydrogen. Well, using pipelines designed for natural gas, which are used nowadays in the existing grid, to transport hydrogen gas in the future cannot be done without further consideration. The pipeline lifetime can be estimated conservatively by using the upper bound of the fatigue crack growth rate database, gathered from experiments using different pipeline steels, grades, and loading conditions. This method is proposed in a recent modification of the ASME code B3112, concerning the fatigue lifetime of pipelines transporting gaseous hydrogen. Data of 4 pipeline steels, 2x52 and 2x70 steels, with gas pressures up to 21 megapascals are shown here in green. The equivalent fatigue crack growth rate in air is displayed in blue, and the red line represents the approximate upper bound of the data, and this is implemented in the new B3112 code. Let's talk about different influences. First one is the frequency. Well, studies indicate a negative correlation between frequency and the fatigue crack growth rate in gaseous hydrogen atmosphere. Hydrogen embrittlement is time dependent, and as hydrogen needs to absorb into a steel microstructure and can diffuse to the crack tip in order to deteriorate the material. As lowering the loading cycle frequency extends the exposure time of the material to the hydrogen gas environment, more atoms of hydrogen are able to absorb in the steel microstructure and can diffuse over longer distances to the crack tip region with each loading cycle. The paper presented here investigated the effect of loading frequency and hydrogen pressure for a vintage and also a modern steel. So a vintage and a modern X52 and 2 modern X70 steels. The crack growth rate per cycle for a fixed delta K of 14 and loading frequencies of 1, 0.1 and 0.01 Hertz are shown. The graph shows that the X52 vintage steel has the smallest sensitivity to loading frequency. There is no real effect to be observed. While the others, they show a modest sensitivity depending on the frequency. As such, the quantitative effect of loading frequency was observed to be material dependent. And this could be explained by the difference in, again, this hydrogen diffusivity. And this is linked to the microstructure. So each steel has a different microstructure, and this comes with a different diffusion coefficient of your hydrogen atom. And this can be the reason why we see these variations upon different grades. Let's continue with more about the material characteristics because they seem to be very important, the microstructure. Generally, people thought there was a link between the strength and the sensitivity of embrittlement. The literature suggests that hydrogen embrittlement degree increases with increasing strength, suggesting a trend of increasing susceptibility with the higher pipeline steel grades, going from X52 to X70 to X100, for instance. One would expect a higher degree of sensitivity with higher strength levels. A lot of studies state that the strength level is a key factor in the sensitivity to hydrogen embrittlement. And also currently, the standardized acceptance criteria for pipeline steels and their welds and hydrogen application, which is the code ASME B3112, they are based on the maximum allowable hardness of the pipeline material. So there you can see the link with the strength level and the hardness. However, when going through the literature, this is somewhat contradictory, but generally, the literature fails to confirm a correlation between the strength and the hydrogen-assisted fatigue crack growth for pipeline steels. It's not the strength and the hardness that is the key factor, it's more the microstructure and the chemistry that dominates the fatigue crack growth behavior in gaseous hydrogen atmosphere. It is therefore not correct that all increases in strength, by definition, leads to inferior hydrogen resistance. Steels of similar strengths are often fabricated also following different heat treatment schedules. And so, because of this, they show a different microstructure. And this will lead not to the same behavior in the hydrogen atmosphere. Therefore, we now have a necessary conservatism in the fitness for service assessment of the existing network. Well, the diffusion is important. This is linked to the microstructure. Well, each microstructural component, phases and microstructures, they show a different behavior when exposed to hydrogen. Absorbed hydrogen atoms, they can diffuse in the steel, and they can get trapped. They can get trapped in a reversible or irreversible manner at trapping sites, at defects in a microstructure. For instance, grain boundaries, dislocations, or other metallurgical defects, for instance, inclusions, non-metallic inclusions, precipitates, or for instance, regions of hard microstructures or segregation lines. The trapping characteristics of these microstructural features will strongly influence the sensitivity to hydrogen embrittlement, as the presence of these traps will affect the kinetics of hydrogen transport, again, the diffusion. For instance, reversible trapping is related to diffusible hydrogen, and this is considered to be the main culprit in hydrogen-assisted degradation phenomena. The existing pipeline system is constructed out of an enormous variety of materials over the years. Different types of pipeline steel grades and grades also produced following different production processes are implemented into the grid. The complexity of making a general assessment of the resistance to hydrogen embrittlement is very difficult, and it's clear by this. A proper evaluation of the sensitivity to hydrogen degradation of the current pipeline system requires understanding of the relation between microstructure and hydrogen-assisted degradation. As you can see here, we see a vintage X56 and a contemporary X70 steel. These materials show a heterogeneous microstructure. You see their bands being present. So they show different trapping characteristics, different diffusion characteristics, and they lead to a different sensitivity to hydrogen embrittlement. In the case of, for instance, charging very severely, which is happening in cathodic overprotection, you can see that the X56 material, here you can see a lot of cracking being present. Most of the cracks hydrogen-induced crack, because this is without mechanical load. We talk about hydrogen-assisted cracking when it's combined with mechanical loading. In this case, it's hydrogen-induced cracking because there is no mechanical load. It's only exposure to the hydrogen atmosphere that already leads to cracking without any additional mechanical loading. Here you can see cracks starting at eminence inclusions, also at perlite or long grain boundaries for the X56. And this X56 material was much more prone, much more sensitive to this Higg formation, although the strength level was lower compared to the X70 material. For the X70, we needed to charge much more hydrogen into that material to evaluate and to observe some cracking, again observed at eminence inclusions or niobium-based carbon nitrides and the segregation hard bands of the material. Let's consider welds now, because welds are also an important factor in the distribution of gaseous hydrogen. Well, pipeline welds, they show critical features compared to the base material. For instance, the presence of stress concentrations are present due to geometrical imperfections. We also have weld flaws, and we can also have poor coating conditions. Next to that, we have critical microstructures being present in a weld because we have different type of microstructures depending going from the filler to the base material with heat affected zones in between. Also, we have a high residual stress. Well, welds and pipelines are typically the region in which most defects can be found. And we know already that defects can interact with hydrogen because they can trap hydrogen, they can affect diffusivity. So these are critical regions. And they should be, or they can be, more sensitive to fatigue crack initiation. However, there is no extensive literature done yet on gaseous hydrogen, and many inconsistencies exist in the literature. We have done some work on this, and here you can see an SEM image of a microscopy image of a weld after in situ constant load tensile testing. So we put a sample under constant load, we let hydrogen diffuse into our samples, and you can nicely see that crack is initiating at the base of the filler. So the filler material on top, there crack initiates, and then it propagates towards heat affected zone 2. This comes with a different microstructure, and this is then the more hard microstructure. But as you can see on the right-hand side, we do thermal desorption plexoscopy. With this method, we can measure the concentration of hydrogen. Well, the filler material contains or can uptake most hydrogen, as you can see in this graph on the right. And this was the reason that crack initiated in the filler material. Much more research is, of course, needed in this field. Let's go to the final influence, the influence of the environmental conditions on hydrogen-assisted fatigue crack growth. Let's start with pressure. Well, as the amount of atomic hydrogen available per unit volume increases, also the localized hydrogen embrittlement effect at the tip of a growing crack are increased. This is because the hydrogen trap occupancy has a strong function of pressure and exhibits a plateau behavior as the traps saturate. An increase of the fatigue crack growth rate with rising hydrogen partial gas pressure is observed in the graph. Moreover, studies indicate that the actual extent of the pressure dependence on the fatigue crack growth varies with the microstructure again. These dependencies make it very challenging. Therefore, it is advised to perform a case-by-case evaluation of typical steel grades found in the system. Moreover, since fatigue testing is very time-consuming and labor-intensive and also very costly, the importance of the development of an adequate screening methodology based on relevant hydrogen characteristics can be of interest. The second parameter is the temperature. Carbon and low alloy steels, they exhibit less severe hydrogen embrittlement as temperature increases. The fatigue crack growth rate was found to be maximum at room temperature. The influence of temperature can be explained based on the hydrogen trapping model, in which hydrogen is considered to diffuse through the material or be trapped with a certain binding energy at these microstructural defects and constituents. At temperature lower than the room temperature, the diffusivity of hydrogen is too slow, too sluggish to substantially accumulate at traps. At high temperatures, hydrogen mobility is strongly enhanced and trapping is diminished, and detrapping is also facilitated. For instance, for underground pipelines operating between 0 and 10 degrees, room temperature experiments can give you conservative results. Another factor are impurities. Addition of specific chemical gas components to a mixture of natural and hydrogen gas shows a lot of potential. Hydrogen gas purity strongly influences the uptake of gaseous hydrogen into a material. As such, depending on the specific gas species, impurities may increase, may have no effect, or may reduce the severity of hydrogen-induced degradation. This is shown in the graph here, where the effect of impurities on the fatigue crack growth behavior of a low alloy steel is shown, relative to the behavior in pure hydrogen, as you can see in the y-axis. Gases like oxygen and carbon monoxide, they show a dominant inhibiting effect when in combination with hydrogen, while, for instance, methane and carbon dioxide had only small effect on the crack propagation when added to hydrogen. However, even though beneficial short-term effects were seen on inhibition through these gas impurity additions, the longer-term benefits of impurities have so far not been studied. Further investigation of impurities and their long-term working could be of great value. Let's go to the conclusions. Well, the exact influence is affected by many parameters, as I explained in my presentation today. For instance, the material chemical composition and the microstructure is very key. Also, the load frequency, the hydrogen gas pressure, and the gas purity play an important role. A method to conservatively estimate the lifetime of a pipeline system is to use an upper bound of the fatigue crack growth rate data gathered from experiments, using different pipeline steel grades and loading conditions. This method is proposed in a new modification of the ASME B 3112 code concerning the fatigue lifetime of pipelines transporting gaseous hydrogen. A lot of studies state that the susceptibility to hydrogen embrittlement increases as the material strength is increasing. However, other authors conclude that the fatigue crack growth response in a hydrogen environment is determined by the pipeline steel and its specific microstructure again, rather than its strength grade. Moreover, over the years, different types of pipeline steel grades and grades produced following different production processes were implemented in the network as well. Attention should be given to the welded connections as well, given their variety of microstructures. The potential presence of weld flaws and also the presence of stress contributions is very important here. And as a final note, the addition of certain gas impurities like oxygen or carbon monoxide to the mixture or to the hydrogen gas shows a lot of potential in inhibiting the hydrogen-assisted degradation of pipeline steels and weld. But again, more research is needed in that field. If you want to read more about this, you can find some more information in this review paper where we evaluated the use of the existing pipeline infrastructure for gaseous hydrogen storage and transport. Thanks a lot for your attention. If there are any questions, please feel free to ask or to contact me after this session.
Very good. Thank you, Tom. This was a very nice overview. Any questions from Gert?
Yeah, thank you for your presentation. This is very interesting because we were also doing some research here on this. And I was wondering, because we are thinking about maybe coatings that could be applied to the existing infrastructure. What do you think about that? Do you think the inhibitors will be so good that no further protection is needed, depending on the different materials that have been used in the existing European grid?
Very relevant question indeed. The coating is an important topic as well, although applying a perfect coating without any flaws can also be very critical. If you then have a coating which is not perfect, then locally you can have an increased and much higher uptake of hydrogen, which can lead to failure. The addition of inhibitors like oxygen or carbon monoxide, they work fine on steel. This has been shown by atomistic simulations as well, because they go into competition with dissociation of hydrogen molecules. So preferentially, your carbon monoxide or your oxygen will react with your surface more than hydrogen molecules can do. So this leads to a lower uptake of atomic hydrogen into your steel microstructure and hence a lower susceptibility to hydrogen embrittlement. However, this is proven, or this is being shown on pure steel, where the interface for the surface is the steel microstructure. When you put a coating on top, this is a totally different story. There is no research yet done on the effectiveness of a coating and the inhibition of these gas impurities, how they can act. Many people claim that with polymer type of coatings, for instance, that these small molecules, they can penetrate over a long time of exposure. So it can be a possibility, but it's not for sure yet.
Thank you very much.
You're welcome.
Yeah, if there are no further questions, thank you, Tom.
Thank you.
Karim.
Yeah, I have one question. You say that hydrogen diffusion is of key importance. It's dominating the flattening mechanism. In the meantime, when you show the effect of temperature on steel, when you increase the temperature, the hydrogen effect is lower. And this is something I didn't get actually.
Yeah. Good point. Indeed, because with higher temperature, your diffusion is faster. And I claim that diffusion is an important property. The thing is, it's linked to the trap occupancy. Also, your detrapping from defects will also be increased. So it's a balance that you get. You have your hydrogen being into your microstructure. It will interact with your defects. So it can be trapped at your defects. So it can locally lower its energy state. But it can also detrap from a trapping site. And that's where you have reversible and irreversible trapping. So if it's reversibly trapped, it means your hydrogen atom can escape again from your trap site, for instance, from your dislocation or from your grain boundary. When it's deeply trapped and, for instance, the coherent interface of a carbide with its matrix, it's irreversibly trapped. However, if you play with temperature, this changes, of course, because an irreversible trap at room temperature is a reversible trap at high temperature, because you give more energy to the atom of hydrogen to escape again from that trapping site. So that's why at room temperature, this is the most severe situation, and this leads then also to conservative results for the operation, because this is done at lower temperature. So if the tests at room temperature are successful and are give trust, we can of course say that at lower temperature it will be okay, also at higher temperature. That's the reason it's not only diffusion, it's combined with detrapping as well, which is then also increased at higher temperature.
Okay, thank you.
You're welcome.
Okay. Maybe 5 minutes more, Karim, for the conclusion of the morning session.
Okay, so I'm gonna try to conclude in 5 minutes what have been said this morning. Show my key takeaways. So this morning.
Thank you, Tom, again.
You're welcome. Thank you.
We had an introduction from Marcel about the technology sheets, and we afterwards got 6 presentations on storage and distribution technology. The first one was about compressed.
Marcel, maybe just me, but I cannot hear anything.
No, there was no sound.
There was no sound, so I will do it again.
Yeah.
Yeah, sorry
Same
about
here.
that. Yeah, can you hear me now?
1 minute. Sorry.
Okay, so this morning we had the presentation, 6 presentations on storage and distribution technology. First one was on compressed hydrogen storage. Second one was on liquid from Davide CEA. Third one was from Earl about ammonia storage, high-tech XL. Fourth one was about Hydrides sorbent storage from Felix Heubner. Fifth one on LOHC from Ton, UMICORE. And the last one was about pipeline distribution from Ton and University. So I'm going to here try to tell here what was my key takeaways from the presentation this morning. About the first technology on compressed hydrogen storage. As for the others technologies, the development are obviously driven by application. I mean, there is some specific development when we talk about stationary storage or when we talk about onboard storage or mobile storage. On the first technology, Marcel showed that there is 4 types of tanks and even a 5th type under development. When we focus on advanced materials storage on 3 and 4 type, it's a lot about metal liner, but on plastic liner, fiber reinforced thermoplastic, but also thermoset-based composite. What I got from your presentation, Marcel, is that Europe has a strong value chain on that type of technologies, even on tanks, integrating tanks, but also supplying materials. You also show that one of the key issues is the hydrogen environment, and this is something also that have been shown by liquids, hydrogen storage, but also for pipeline distribution. That was for the first technology. On the second technology about liquid hydrogen storage, so Davide showed us a lot of application from ground installation, mobile user space applications, and so on. And what I got is that usually, made of aluminum and lithium. And where there is room for development of material or advanced materials solution is for aircraft application, mainly on liner and structural elements. We show that mechanical performance are key. And one of the key issues is to get materials that can sustain high strength, but also versus density. You show that there is the same tendency that what we got on compressed technology. We go more and more on tanks based on the CRFP, composite materials. That was for the second technology. Third technology about ammonia distribution. So I'm happy to know now that the nitrogen that I got in my body comes from different plants. Thank you, Earl. But what you show is that that there is some current use of ammonia today as fertilizers, feedstock, but the future use will be also on as an energy carrier, as a hydrogen carrier, but also as transportation fuel. And you show that there will be a high demand of ammonia for the maritime applications. You showed that there is several storage methods, pressurized, insulated, semi-refrigerated storage, and different mode of storage, pipeline, rail tank, and so on. There was some question about NOx. Also, you highlighted the issue about safety, but you also said that safety is not a big deal, as we have a very nice, we have a capabilities as human to smell it very easily. And one thing I need to say also about ammonia, if I talk about materials, is about ammonia cracking. We still need some catalysts to crack ammonia, and today they are based on ruthenium. So it's still an issue for storage of hydrogen via ammonia. Fourth, technology about hydrides and sorbents. So my key takeaways here is that there is many materials that can absorb at low gas pressure, and you can, deliver. You can store more than what you can store by liquid or high pressure hydrogen. It is safe because you highlighted that it's a chemical reaction, so you can store it. In a safe way. You can store hydrogen in a safe way. But you also said that there is some issue on cost as the absorption. But you also said, sorry, that as absorption is exothermic and desorption is endothermic, we should care a lot on thermal management, and especially on an integration of the technology into the systems. You also highlighted the issue about volume expansion, and you also said that there will be some, one of key solution would be to monitor the materials, especially by developing digital twin of materials. One of the main problems that was raised also by one of the attendees is the kinetics. Yeah. But of course, it depends on materials. Yes. Then we got a talk from Ton about LOHC. What I understood is it's quite, you can store a quite useful amount of hydrogen on LOHC. This is quite safe. I felt that there is no issues on materials development, but I think there's still some issues on catalyst development. You show some issues about platinum, and it will be, what I understood now, correct me if I'm wrong, it will be hard to get rid of catalysts for such an application. And one of the slides that Ton showed is that the amount of platinum that will be needed is not that big, so it can be manageable. So that was for the LOHC. Oh yeah, of course, I forgot something. One of the main problems of LOHC was about thermodynamics. It's also an issue about endothermic reaction, exothermic reaction, and you also emphasize this about the energy system integration to optimize the overall efficiency of the process. And last one was the presentation from Tom, Penn University. Very interesting presentation on the influence of hydrogen on pipeline steel. Was clearly on hydrogen embrotillement. You showed an estimation of the pipeline lifetime transportation. You also said that there is an enormous variety of steel. So each, I would say, nuance of steel deserves a specific study. One of my key takeaways is that it's not about only strengths. One of the key fatigue mechanism come from the microstructure. We have to show, we have to look at the microstructure, but also on the chemistry. One interesting thing was about also the weld defects. What will be the hydrogen influence on the weld defects? And one of the solutions you probably show is about potentially using oxygen or carbon monoxide as inhibitors for such application. And I think that's it for my wrap up.
Excellent. Thank you, Karim. This concludes the morning part, and
we will start again at 1:30. Try to have enough time in the afternoon, so more than enough time to have a big coffee and a small sandwich.
So we come back at 1:30.
Thank you, everyone.
Thank you.
Thank you very much.
And enjoy the sandwich or whatever. Thank you again.
Thank you. Bye-bye.
Thank you. Bye.
Thank you.